Hi class, welcome back to our discussion of metamorphic rocks. We're going to speak specifically about different types of metamorphism. So we've gone through classifying metamorphic rocks, what makes a metamorphic rock, pressures and temperature changes, right? We've talked about how we kind of quantify facies with pressures and temperatures, or how we think about intensity based on the minerals that are present. And now we want to kind of put rocks into the tectonic environments that they might form in, and talk about them a little bit more, metamorphic rocks a little bit more there. So we'll cover these 5 different types of metamorphism, some of them in more detail than others because they're more complicated. So shock metamorphism and ultra high pressure I'll briefly touch on, but I'll spend more time on regional and say metasomatism or hydrothermal metamorphism. Okay? So regional metamorphism is going to occur at a convergent plate boundary. This is where we have a lot of activity going on. A lot of heat is being moved to the system. A lot of mass is being moved to the system through melting. And the first thing to think about here is the temperature distribution within this region. We see a subducting lithosphere. We see an overriding plate here. Okay? And then we see these pink lines. These pink lines are called isotherms. Iso meaning constant, therm referring to temperature. So everywhere along this line, we see a change in its orientation, right, as we move from sort of horizontal to steep to this peak. No, but it's always 300 degrees. And so when we move down in any place through this system vertically, we hit a different kind of arrangement of these isotherms, right? Here 600 and 300 are pushed up around this line C, where you move down. Here they're depressed down, and here 600 and 300 are pushed way down. Okay, so this is going to affect the paths that the rocks experience, the pressures and temperatures that they experience to some degree. So these isotherms are important for thinking about, let's say, those 3 paths we talked about rocks could move through, right? Low temperature, high pressure, high temperature, low pressure, and then the regional metamorphism, which could reach both high temperatures and high pressures. Okay. So in a convergent boundary, we have some metamorphism that's going on because we have rocks being pushed down into the Earth's interior that are part of the subducting lithosphere. So we're increasing pressure and we're increasing temperature on those rocks. Okay? Those rocks are cold ocean rocks, so they're not very warm. There's no heat source out here. And as they move down, they retain that cold temperature. So they heat up very slowly. And that has the effect of depressing the isotherms in this region. So these rocks that are moving down, and I'll get my pen out here, that are moving down like this in this slab, they're going to be following the high pressure, because the pressure is going up, low temperature path. Okay, so that's the rocks here at A. So they're at the high P, low T. Okay, high P, low T. There's no good source of heat. All the heat's being conducted into the system, and it's relatively slow. Now, that's for what we call blue schist rocks. So blue schist rocks tend to be ocean rocks, oceanic crust, mafic rocks, basalts that are being subducted. Also, we find the accretionary wedge here, which we talked about in tectonics. Those rocks can also be sucked down into this boundary between the overriding continental plate or oceanic plate and the sinking or descending oceanic lithosphere. If we move to the right here, we know that from igneous rocks we have melting, in this case wet melting, which produces magmas that rise up and collect in the crust. And so what's happening there is that we're putting heat from down here up into the cooler crust, and that is causing a deflection up. That's pushing these isotherms up, and it's pushing them really close together. So we're going to heat up this region of the crust, and that's going to give us a regional path. Okay. Regional path where we can reach high pressures and high temperatures. Okay. So heat moves up, it warms up the crust. These rocks are under stress, they're being compressed, right? It's part of the process of forming a foliation. Okay? And then if we looked at one of these individual plutons here, we'll talk about this later, we could talk about what we call contact metamorphism. Okay? So here we've got high pressure, high temperature. Here we have high pressure, low temperature in the subduction zone itself. And then out here we have this sort of natural stable conditions. Okay? If I turned off this subduction process, the subducting lithosphere, what would happen to, and the melting that's going on here, what would happen to these lines? Well, over time, heat would redistribute and they would become horizontal. So over time, we would see the lines straighten out and come straight across the diagram like that. Okay, so this is all part of regional metamorphism. We get blue schist grade, we get high pressure, high temperature regional metamorphism at convergent boundaries. Okay, at convergent boundaries, that's where we'd expect regional metamorphism. We can take a look at the different facies, and we talked about facies a little bit. So here are some different facies. These are the facies names, and we don't have to worry about all of them. But you can see blue schist we talked about. Where are the blue schist rocks? Those are number 3 right here. Okay, here's zone 3, blue schist. Okay, high pressure, low temperature. Where's green schist or amphibolite? Those guys are 5 and 6. Okay, so here's 5, right? And then if we go deeper, where we have higher pressures and temperatures, we're going to go down to 6. Amphibolite grade is higher grade. 6, right down there. We go deeper, and we get into down here at 8. We get to those ultra high pressures of granulite grade metamorphism, right? So top to bottom, then it makes sense that we go from low intensity at the surface at 1 down to high intensity or high grade at the base. So, you know, we live in Illinois, and the base of Illinois, the crust here should have some granulite rocks at it. And if the deeper you go, the higher the grade. The difference is that those metamorphic rocks formed a long time ago, so we're not forming them today. They're you know, the thermal environment here is not changing very much because we have no energy input from magmas. We have not a lot of deep tectonic activity. Okay? Ultra high pressure metamorphism refers to this granulite grade metamorphism, okay, happening at the base of the crust. We see specific examples, and I've thrown this in here as a specific example of index minerals, pyroxenes and garnets, okay, that are found in these rocks. They're sometimes called Christmas tree rocks, okay, primarily made of pyroxenes and garnets, and that combination of minerals tells us that this rock was metamorphosed at ultra high pressures and temperatures. If I back up, physically, where is that? Well, let's figure it out. 8 would be granulite, okay? So where are we? We're down here at the base of the crust, okay? The base of the crust in the deepest areas where we're getting the most magma heating up the base of the crust, okay? And so this is just a repeat of the previous diagram I showed you. Okay, so that's regional metamorphism and ultra high pressure metamorphism. Okay, contact metamorphism happens around plutons. It happens around igneous rocks. So here's an igneous rock right here. It's a granite. As it cools, it gives off heat, and that heat is conducted into the surrounding, what we call host rocks. So the rocks that surround the igneous blob are host rocks, and they get cooked. They get cooked without differential stress, which means we're gonna primarily look at rocks that have seen grains get bigger but no foliation form. Okay, so we might expect to find non-foliated rocks around an intrusion, but the contact refers to the contact between the hot rock here and the cool rock, okay, out to the side. And this area of metamorphism is not very big. Okay? Regional metamorphism is happening top to bottom through the crust and over sections of the crust that might be 200 to 400 kilometers wide. So big volumes of the crust. How big is this rind here? Sort of like, oops daisy, is this rind here around the around the Pluton? Yeah, it's maybe 1 or 2 kilometers. Okay, not 100 kilometers, not 10 kilometers, it's 1 or 2 kilometers. So it tends to be very thin. So contact metamorphism is local, okay, local to intrusions. Shock metamorphism, you can imagine, is somewhat rare because we don't have a lot of impacts being creating big craters today. There are meteorites, they're not uncommon, that come into the Earth's atmosphere, but a lot of times they tend to kind of explode because of the atmospheric pressure. It's just they're too big, too small and too weak for the pressures and temperatures that are being exerted on them as they enter the atmosphere, and they blow up essentially. So they don't have a chance to make a crater. But if they did make a crater, what we'd expect to find are these little minerals here of stishovite. Okay, we'd expect to find other kinds of rocks that are associated with impacts, tektites. If you're from Illinois, okay, I will tell you that in Des Plaines, there is a meteorite impact crater underground. It's under all the glacial till, but people have looked for these kinds of tektitic rocks, which are called shatter cones. They're associated with high pressure, high temperature impacts and shattering. And I don't know if anyone's found stishovite, which is a polymorph of quartz, but ultimately people are studying these big craters and thinking about the minerals that should be present there, and people were studying the presence or the stability of stishovite in the Earth's crust, and they said, well, the pressures and temperatures of a meteorite impact are so high that they could represent or reproduce conditions in the Earth's interior, let's say granulite grade conditions even, right? And so people went to look, I can't remember the name of the mineralogist who went to look at the craters and found that, yeah, sure, we find stishovite in these impact craters, and it sort of works as evidence that they are, of course, impact craters. Now, sometimes you also find the meteorite itself. Yeah. Metasomatism or hydrothermal alteration is occurring as a function of a fluid moving through a rock. That could be CO2, but it's usually a combination of CO2 and a lot of water is involved here. Magmas carry water themselves, okay, so they can drive this process as they crystallize. They give off water into their surrounding rocks, and that creates metasomatism. Water facilitates transport and the movement of mass, but we can also have water come in, we call meteoric water coming in, so rainwater, groundwater intruding into these rocks, interacting with them, and then redepositing minerals and elements. The idea here then, if you look at the convergent boundary, is a place for really, there's a lot of hydrothermal alteration that goes on. The ocean crust, right, forms at the mid-ocean ridge. It sits on the ocean floor. It's altered by water, which infiltrates and reacts with the rocks. The wedge is altered by water, okay, from the ocean. And then plutons themselves and water from the mantle leaks up into the continental crust in this convergence zone and will lead to the formation and deposition of things like gold, silver, copper, right? All of these mineral deposits in South America, in North America, in the southwestern U.S., they are related to or somehow connected to hydrothermal processes where water helps to concentrate base metals and precious metals. Okay? Right at the ridge, we have a lot of water infiltrating because the crust is thin, it's hot, we have a lot of cracks, and so water can penetrate down into these cracks, interact with the magma chamber, and we actually have ore deposits that we think are parts of oceanic crust, which has been pushed up onto the Earth's surface through a process of abduction, or it's been sandwiched between two converging plates, or along a fault, and that there are so essentially deposits on the ocean floor of things like zinc, lead, copper, silver, gold, right? Hard to access a few kilometers down, but easy once it's on the Earth's Earth's surface. Okay? Usually by the time the rocks get to the Earth's surface, they're pretty messed up, and so figuring out their history can be tough. They tend to be pretty old, commonly hundreds of millions or even billions of years old. Okay, if you look closely at a Pluton, here's our Pluton. We can have water come out of the Pluton. My pen going. Come out of the Pluton and head up and really take elements from the Pluton and put them into the host rocks. We can also have meteoric water that's moving down through fractures. It comes down, it gets hot. Hot water is able to dissolve elements and minerals more readily, and it drives it up because it's hot. Why is it rising up? Because of buoyancy. Water is expanding. It's lower density than the rock. And as it cools, those elements come out of solution and form solid materials. So here we see like a zinc sulfide or pyritic, sphalerite chalcopyrite vein that would have been an open fracture that water would have moved through, and with time, as the water's moving through it, it's constantly sort of depositing scale of these elements on the margins. And this is where many of the deposits, as I said, in South America, in the western U.S. Have come from, through this hydrothermal alteration. It's an essential process in forming natural resources, base metals and precious metals. All right, so in summary, we talked about the conditions that have led to metamorphism, characterization of metamorphic rocks, different types of protoliths, what parent rocks are, right? The starting rock. If you start out with a siltstone or a mudstone, you're going to get a schist probably, most likely. We talked a little bit about metamorphic grade and how to recognize that. We talked a little bit about pressure and temperature. We didn't talk about time paths in this section, but it's really about putting a clock on how long it takes for a rock to go down and come back up. And then we talked about metamorphic events, types of metamorphism, regional, which could also include ultra high pressure temperature metamorphism, contact metamorphism, shock metamorphism, and hydrothermal metamorphism.